Yeah, before we start our first project, just additional chapter was the most important block. There was an old chapter 3.7.6 just dealing with DT1. I have cancelled it because DT1 is not really important for us. So I have done this in the past, but now to save time, I just continue with the PI controller. It's not normally, the name is not PI block because the PI is a typical block which is used for a controller. I really not know any other application for a PI block than a controller. So I give the name PI controller. And I would start first with the simple circuit. There is again inverting amplifier, 3 components plus operational amplifier. We assume again ideal amplifier with hidden minus sign. With R1 as the input resistance, and now in the feedback we now add two components in series connection, a resistance and a capacitance in series connection, R2 and C. This is PI controller, the typical circuit, simple realized with 1 operational amplifier, 2 resistors, 1 capacitance, and then you have a PI controller really working in any hardware condition. To discuss a PI controller, we need the transfer function. Again, U2 over U1 is Z2 over Z1. Z2, the feedback impedance, is the sum of the series connection elements. This is R2 divided by 1 plus PC, and divided by the input impedance R1. I want to have only one division line, so I multiply numerator and denominator with PC and get the 1 plus PC R2 divided by PC R1. If we look into the page 16 of my workbook, look on the PI page, PI row, that is row number 9, then you see there is this slight difference in the transfer function. You see numerator and denominator time constant is the same, and here we have an additional k in this element. So this is not the normalized form. The normalized form want to have the same time constant in the numerator, in the denominator that we have in the numerator. In the numerator we have C times RC. We cannot change it because of this one. So this is the time constant with the name Tn used in workbook page 16. To get here a Tn, we have just to expand this expression 1 plus PCR2. If we want here to have PCR2, then we have to correct it. So we have to correct this by multiplying the numerator with R2, and the R1 is just extracted into the front. So we have here R2 over R1. This is a constant factor. We can call K index C because this is what we can later call controller gain. And this here then is now the same time constant that we can find in the numerator. Now this is Tn. So that we finally have the controller gain numerator 1 plus Ptn divided by Ptn. That is one of the well-known, because it's Bode form of the PI, Bode form of PI controller. Sometimes there is another typical form of the PI which can be calculated if we now separate the numerator polynomial function. So we can say this is Kc divided by Ptn, Kc divided by Ptn, that is the integrating part, plus Kc times Ptn divided by Ptn, that is just Kc. And if you look what is Kc divided by Ptn, then we can find Kc divided by Ptn. The factor Kc divided by Tn though is R2 over R1 Kc divided by, and Tn is C times R2, C times R2. Then this is R2 can be eliminated, 1 divided by R1C. That is a time constant different to Tn, which I can call Ti. That is the, here you see the original denominator time constant, Ti. And I can say, okay, this is 1 divided by Pti plus Kc. So, later I will show you in symbols, this is the summing form of a PI. Summing form or parallel form of PI. Some people prefer this, other people prefer this, or with this you can draw the Bode plot very good, with this you can calculate the step response very good. So depending on the application, one or the other is more suitable. Okay, let's take some minutes for the step response of a PI. Again, the U2 of P, output of the step response, is step function at the input multiplied with transfer function. And I have mentioned the Bode form is good for Bode plot drawing. This, you will see, is very suitable to draw the step response, because the summing form can then be solved separately for each part of the sum. So frequency function, inverse Laplace transformation, U2 of t is, you see, the first part, Kc times U sub O divided by P, is what? It is U sub O parenthesis. Then Kc divided by P is Kc divided by step function. 1 over P is step function, plus U sub O multiplied with 1 divided by P times P is P squared times Te is ramp function divided by Ti time constant. So this leads to the following function. Note that Ti, there is an equation, Ti depends together with Tn and Kc. If I solve this to Ti, this is the inverse of this, is Tn divided by Kc, so that we can write the step response also with the following expression, depending on now using the Tn, U sub O times Kc times step function plus Kc times T divided by Tn. So now I have replaced Ti with this, so then the Tn is in the denominator and Kc is in the numerator. The drawing of the step response is a typical step response of a PI looking like the following curve: 0 for starting phase for negative times. So note that if you measure the step response, first you have to unload the capacitor to reach these initial conditions. Yeah, you can say here unload C. That you have to force. It comes not for itself. You have to do something to short circuit cable, connect to the capacitor, unload it. Then you get 0 starting voltage. Then the first moment the ramp has no effect. You have only the step function, and the step amplitude then is this, and this is then Kc times U sub O. And then the ramp is starting, and what we can find out is that a good value is if T is Tn, then the increase has the same amount than Kc2, the starting value. So I measure this distance, I double it, so this is 2 Kc times U sub O, and this time then we can call here Tn. Or in other words, if I go back, extrapolate the ramp function to negative t values, this is the time negative Tn. So this is a way to identify parameters out of a measurement, measure this curve, make an extrapolation, and the cutting point at the negative t-axis defines the Tn value, and this defines the Kc value if U sub O is measured. Yeah, that is the amplitude of the step function. This leads to the symbol of a PI, which is two versions available. One version is this. This is top left parameter Kc Tn. Parameter. A PI is defined with these both two parameters. Again, if we have an automatically reading system for symbols, this could be mixed with my integrating symbol, because then the distance here defines the difference. So better, I prefer sometimes, it's more unique. The mix up is then more difficult. I prefer this symbol with the same parameters in the top right and top left position. In both cases we have a PI. In some programs you can find this, in some other programs you can find this. So both have the same meaning. Okay, this is my PI block. Kc is called the controller gain. The question is this a DC gain? How large is the DC gain? How can we find it out? Not with the step response, but with the transfer function. If you look here into the transfer function, here this position, and want to use the calculation, want to calculate the DC gain, set P to 0. Yeah? P0, the frequency value of 0 is the DC gain, DC for direct current, for constant values. Battery has DC voltage. If P0, you see the numerator is not 0, but the denominator is 0, so then this goes to infinity. So the Kc cannot be the controller gain. DC gain is infinity. And Kc controller gain is the high frequency gain. You will see in the border plot. High frec gain. Yeah, finalize with the discussion of the PI controller with the border plot. the steps we have done several times. The complex frequency transfer frequency for complex frequency response is Kc times 1 plus p replaced by j omega, so j omega Tn divided by j omega Tn. The magnitude curve depends on the magnitude function. If I calculate the magnitude function, I have a division line. In the denominator, we have only the imaginary part, so the magnitude is the imaginary part itself. And in the denominator, we have a Kc, and then the one real part plus j omega Tn, this is an imaginary part. We have square root with Pythagoras 1 plus omega Tn squared. And the phase is again the phase of the numerator minus the phase of the denominator. The denominator is simple, just an imaginary part. A pure imaginary part has a phase 90 degree. In denominator we have a minus 90 degree part, plus arctangent, a 1 plus j omega Tn gives an arctangent omega Tn value. So this is the phase equation of the PI, this is the magnitude equation of the PI. Those elements are very important for the controller design method described in chapter 5. But now a Bode plot. If we have done this several times, you see the result then can be more and more written or sketched in a quick way. We use again the asymptotical construction. The magnitude curve for the small frequencies, very small frequencies, if omega is small compared with 1 over Tn, leads to the fact that if this is small, you can neglect this compared with the 1. Square root 1 is 1, so we have approximately a Kc divided by omega Tn. It is an I part. So we can see for low frequencies the Pi behaves like an integrator. For high frequencies, omega is large compared with 1 over Tn. If omega is very large compared with 1 over Tn, then in this expression this becomes large, 1 is neglectable, square root of this is an omega Tn divided by omega Tn, this is 1, and just we have the gain Kc. For high frequencies, that is the P part. So Pi means for low frequencies integrator, high frequencies proportional behavior. So we indicate this with a horizontal line for high frequencies. The distance of this line, note that this is 0 dB, the 0 dB line. This is Kc in dB. Then we have an integrating part for low frequencies. Integrating part, and in the range of where these both approximations are not valid, we indicate this with dotted asymptotical curves. The cross point, again, we have done this several times, is at corner frequencies of the Pi controller, 1 over Tn, and the correct curve then is just a smooth curve here, and the distance between corner frequency, the cross point of the asymptotic curves to the correct curve is again always the same, plus 3 dB. This is negative 20 dB over decade. So the gradient is again, as we know from the integrator. So the high frequency gain, as I have mentioned, is here. It's a controller gain, which we call Kc. And if the frequency is smaller and smaller, then we have more and more the behavior of an integrator. So far, phase curve finally can be drawn in the following way. This is the phase of the pi. Is always negative. So the omega axis should be in the top region of this diagram. We have phase values going to negative values maximum at 90 degrees at corner frequency. How large is the value at corner frequency? If omega is 1 over Tn, omega is 1 over Tn, this is 1, arctangent 1 is plus 45 degrees, minus 90 gives minus 45 degrees. So minus 45 degrees. For low frequencies, this is 0. This is 0. For high frequencies, this approaches the plus 90 degree value. So the phase is now coming from the minus 90 value through this point and approaching the 0 degree level on the axis. So we have a phase curve. The shape of the phase curve is always identical to PT1 and PD, and this phase is always the arctangent curve, but now shifted into the negative area of the phase diagram. So far.